As mathematicians, we strive for elegance, with admiration for ingenious proofs which achieve their objectives with immediacy and beauty. And ultimate elegance is achieved by a proof without words. And of course, just like any ideal, elegance is not always achieved. However, let's look at a few proofs with undeniable elegance. Theorem: if n is a positive integer, then the sum of integers up to n equals half n times n plus 1. Now with this we can look at specific cases, such as, for example, n equals 6, and we can add all the positive integers up to 6. On the left hand side, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. Meanwhile, the right hand side is half of 6 times 7, which is also 21. So for the case of n equals 6, this theorem works, which is great. But only fools jump into conclusions based on one single case. Instead, we need to prove this proposition using a universal proof. So here we're going to look at a stair-step configuration by first drawing a rectangle with the dimensions n and n plus 1. The area of the rectangle would be n times n plus 1. Now the stair-step area would be half n times n plus 1. Let's see how we got this. So we're going to make a stair-step configuration with 1 block, 2 block, 3 block, 4 blocks, and so on. And as you can see, this is actually half the rectangular area. And what we have basically done here is added 1 plus 2 plus 3 plus 4 up until the rectangular side n, and we've also concluded that the stair-step area is half n plus 1. Therefore, we have proved our theorem that the sum of integers up to n equals half n times n plus 1. Let's begin now with experimenting. Suppose we begin with 1 and add the consecutive odd integers, and no matter how long we keep adding the next consecutive odd integer, we realize that the result is always a perfect square. Let's look into this. Starting with 1, 1 squared is 1. Adding 3 will make 4, which is 2 squared. 4 plus 5 is 9, which is 3 squared, and so on. Now, as we can see, that adding a consecutive odd number will always result in a perfect square. But the question is, how do we actually prove this? We're going to use a bit of algebra for this argument. You guys can observe that even numbers can take the form of 2n, right? Whereas odd numbers are 1 less than the multiple of 2, so it will take the form 2n minus 1 for some whole number n. Theorem: the sum of consecutive odd integers starting at 1 is a perfect square. We're now going to look at how to prove this. So firstly, we're going to let s be the sum of consecutive odd integers from 1 to 2n minus 1, which is 1 plus 3 plus 5 plus 7 plus blah 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 plus blah 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 2n minus 1. If you think about it, s is also basically taking the sum of all integers from 1 to 2n and subtracting the sum of all of the even numbers up to 2n. And we can further factorize what we're subtracting by taking the 2 out. Alright, now looking at the first set of brackets, we can see that it contains the sum of all whole numbers up to 2n. And within the second bracket, the sum of all whole numbers up to n. Now, using the theorem we just learned, we can apply the result twice. So the first bracket becomes a half 2n times 2n plus 1, and the second bracket becomes a half n plus 1 with the 2 outside. Now, after a bit of simplifying, we reach this stage, and by just multiplying the brackets out, you can see that s equals 2n squared plus n minus n squared minus n, and that subsequently leads to n squared, proving our theorem that s equals a perfect square, always. That was pretty elegant, but there is a shorter alternative that holds even more elegance, even more elegant than this dog. We're going to show this proof using a special arrangement using a square. We start with a 1 by 1 square in the bottom left corner, surrounded with 3 shaded blocks, and make a 2 by 2 square. 5 unshaded blocks surround it to make 3 by 3, and the process repeats. This simple diagram shows that the sum of consecutive odd integers will always yield a geometric square. There is not always elegance in every proof, where we have proofs consisting of 2,000 pages. However, these no-word elegant proofs are compelling to all modern mathematicians.